Here's the inertial mass balance calibrated for 12.500 Hz, plus or minus one least significant digit. The frequency counter does have additional digits of resolution that are not necessary for the accuracy of this balance. So what we're going to do to test out if there's a difference in thermal accumulation of inertial mass in this bismuth sample, which weighs 10.0000 grams gravitationally, is we'll insert it into the test platform hole and check it at room temperature to see what the frequency is. And then it will be heated outside the balance and reinserted, brought up to 100 degrees Celsius, and we'll see if in fact there is a difference due to the thermal energy that has been absorbed.
In this clip, what I want to do is just look at the number of swings that show up here, like the actual number of swings when it's cold or at room temperature versus when it's hot. The temperature reading here, according to this thermometer, is 20 degrees Celsius. There's sand in here. I'll do this 2 times. $33. One more time. $33. So now I'm going to heat this up. Like this. Just take that off until it's hot. This thermometer here is reading 93 degrees Celsius, just here under the surface, which is showing 130 degrees on the surface. And springs here, the steel arms, 18. There's no thermal differentials there. Okay, let's try this out. $34, $35, $36, $37, $38. $34, $35, $36. So there's 2 or 3 more swings here. $37. It's reading 82 degrees. It's probably cooled down quite a bit already. It's always fun to look at these thermal images. 80 degrees surroundings. Pretty even. So what just happened here? Well, comparing the values of frequency between cool and hot, we see a marginal difference. About a 2.5 decrease in inertia since the frequency increased slightly. However, it is a marginal difference and with an error. What is strikingly different is the decay time, which has increased, and also the number of swings. But before you write this off as simply reduced drag from hot air, see what happens next with water, then aluminum, and a final revisit on the bismuth results. A quick overview of the water test. So in this sealed plastic container, you can see there's some paper towel in there that's wet, and then I have a thermometer probe, a sensor in there, indicated here 19.4 Celsius. So everything is the same. Heat lamp is, as you can see, it's right up against, not making contact here, but it's pretty close to the back, so it's going to heat the back of this wet paper towel inside the container. So first I'll do a cold test here. Ten, 20, 21, 22, 23 seconds. Yeah, I wanted to try a bigger container to get a more pronounced effect. Looks like the same, 22, 23. All right, so now I will start to warm this up here. 74 degrees, it's getting hot. It's probably not going to last too much longer. Oops, let me try that again. I forgot to mention there's a silicone seal around this container. So it's quite airtight, watertight, so it's good container. It's not a perfect seal because I got this little cord going in there, but keeps damn near all of the water vapor in there. So 5, 10, 15, maybe 19 seconds. I'm going to turn the lamp off now. I'll try it again. Let me just fix this here. Okay. 75.3 degrees on the thermometer. This is saying 93 degrees inside. Well, that's probably coming through from the heat lamp. The heat lamp's reading 140 degrees. Twenty, 21. And I also had to use the paper towel in there just to stop because with water, the water would slosh around and could interfere with the momentum and steal energy from it. So that's why the paper towel. 5, 10, 15, 20 seconds. So it looks like that's where it is. So we started with about 23 at room temperature. So looks like I could conclude for the sake of consistency that the motion is being slightly retarded. 15, 20 as it gets hotter, because that's what older experiments showed me. So that motion or acceleration was retarded, slowed down. And I'll just do one more thing here. So the heat lamp is still very hot, as you can see here. I'll just move it out of the way and have a look at the spring steel here. See that it's hardly distinguishable. So according to this, those spots there where the spring steel is, saying 22, 23 degrees Celsius. So these are not, and they're also cool to the touch. In case someone is thinking that this spring steel or steel just heats up and then it changes its spring constant. So yeah, this is not showing any significant deviation here. So, but I'll show you, this is kind of interesting here. So if I just put my fingers on there for a minute, well, a few seconds. Watch this. You'll be able to see that hot spot there. That's from my fingers. 24 degrees or so. So the behavior of the water in this case is a little bit puzzling, because I would have thought that it would have taken longer to complete all its cycles, oscillations, like in the other cases. This is my first interpretation, but I don't yet know, because this apparatus is not sensitive enough to detect changes in inertial mass in the order of a few grams or less. But I plan on revisiting the larger torsion balance type experiments with a more reliable setup in the near future. For now, this unknown effect looks like a drag factor against space-time or the vacuum. The reason I think this is because of the conflicting data that does not support the idea of simple air viscosity changes. This should become more evident as we take a look at what happens with aluminum, and then a revisitation of bismuth. So here I follow basically the same procedure, except in this case I heated the aluminum on a hot plate. As you see here, the averages, which were the result of numerous trials. Notice the first couple of values here are substantially lower because they are immediately following the heating of the bar. And we can also see the similar trend compared to the water, where there is a reduction in both the decay time and the number of cycles of oscillation. I think the aluminum bar in this case is probably too heavy for this apparatus, because it seemed to produce more variance in the numbers, which is why I took more samples. So here is the data I obtained from the previous video on the bismuth disc, and notice the increase there in number of swings and decay time when it was heated, and the frequency actually stayed about the same within error of like plus or minus one swing or 1 second decay time. Now strangely, this seems to be the opposite of what happened with the aluminum bar, but also aligns with what happened with the sand. I don't yet have a clear explanation or theory as to why there's a difference between these materials. My current thinking, though, is that it's related to the heat capacity. Then there's also thermal conductivity differences, with bismuth and aluminum greatly exceeding the other two. Although this doesn't by itself fit the bill for an explanation, I've also considered nuclear spin orientation as a cause, but other ideas are welcome. As I get more understanding about this phenomenon in the future, I will likely post more videos about this or content, so be sure you're subscribed and have clicked the notification icon. Thanks again.